I'd like to introduce Sean Gillis. Be talking about Rasterio, Raster.io. I'll let you tell us. Thank you.
Okay, hi, good morning, and thanks for coming to my talk. I work at Mapbox, and I'm the only person there that doesn't say Rasterio. And I say Raster.io. So we're going to see. I think I'm probably going to lose on the pronunciation of it eventually. But I'm not sold on what it's going to be. I've been a Python programmer since 2001, and a GIS analyst and programmer since about 1999. And I had a bit of a séjour in the digital classics for some years, and so now I'm back doing geospatial stuff. This is my first SciPY conference, and I'm really excited to be here. All right, so my talk is organized around 4 questions. The first being, what's the context for this software development, approaches we're using at Mapbox to solve some of our problems, why we're writing new software to do stuff when there's actually Python GIS software out there already, and then I'm going to explain, after I've convinced you that it's worth trying and worth checking out, I'm going to try to explain basically how you use it, some of the features in it that you don't find in existing GIS software. So I'm going to try to rush through talking about Mapbox's Cloudless Atlas project. And I'm really fortunate to follow Tyler because he's explained basically everything you need to know in the background about Landsat and data issues. We're making a cloudless Landsat mosaic of the world, primarily as a base layer for users' maps, so they can put their own features on top of it and whatnot. Its primary requirements are to be current and to look good. So it's not a science product. It's very, very much about just revealing the features of the world and letting developers come up with maps that can play off the features in the world. It's not something that you can run a model on or do calculations of vegetation indexes and that thing. That doesn't rule out that we'll be working on science products in the future. Now, this is the project that drives a lot of the Raster.io development, and it has a bunch of interesting technical problems, 2 of them that I'm going to talk about quickly. So, if I can go back there. So there's Cloudless. This is Gibraltar, right? The west of the Mediterranean. And we're making it from cloudy scenes. So any Landsat scene of the world is, I shouldn't say any, but most of them have cloud. Depending, it varies a bit on the location and all, but generally cloudy scenes we have to start with. And the first technical problem in making the Cloudless Atlas is getting these clouds out and getting them out everywhere. So with minimal operator intervention. Some traditional methods for making mosaics where you might take, let's say you fly 2 areas and you have 2 scenes and you want to splice them together. Well, you might have a GIS analyst draw a cut line and then you overlay them along the cut line. And this doesn't scale to large data sets, having that kind of human intervention in the loop. And so the Cloudless Atlas needs to scale, because once we get the bugs out here, we're going to run it almost continuously as new data comes in. And at that point, we don't want to have anybody in there tracing and whatnot. So pixel by pixel approaches are what we would really like to do because they scale trivially, right? You can chop them up into any size of piece and offload it to any, and then merge it back in. So that approach worked very well for MODIS imagery. Excuse me. And clearly it's not going to work for very high resolution imagery. Like if you've got a sub-meter imager and you try to do this, it's going to fail spectacularly. Will it work for Landsat? We didn't really know at the outset. So no cut lines, pixel by pixel. So our approach right now is to score the pixels and sort the best ones to the top, because sorting is fairly cheap. Especially compared to tracing and any kind of spatial analysis on your imagery. So this shows, if you can remember before I showed the individual scenes, these are the best pixels by some primitive measure in this case. Every scene has the same extents as the original scenes. We're just sorting the pixels, so in this case, the darkest ones go to the top. Those are the best ones here. Oop, excuse me. And the worst ones go to the end of the stack. So this is where the clouds and the no data values go. So this is just kind of an illustration of the sorting. Also, it kind of shows how cloudy some places actually in the area are. So the second technical problem kind of begins here. Earth's a cloudy place. I mean, over land, even the places we think of as being bone dry and blue sky are 50% cloudy, and up to 70% over more cloudy areas of the land. So Landsat 8, which has been up for almost a year and a half or so, doesn't yet have enough cloud-free imagery that we can make a mosaic, right? It hasn't revisited Hawaii often enough in a dry season to get cloudless pixels everywhere. So we have to use Landsat 7. And Landsat 7 imagery has problems. Its scanline corrector, stop me if you know how this works, but the imager has the satellite's descending over the planet, and it's got an imager that's going back and forth across its path, and it compensates for the forward motion to kind of back up a little bit as it goes. So it would, when operating correctly, it just kind of little push broom thing all across the Earth. Well, that failed in May of 2003, after which it kind of zigzags across the scene, and you get a combination of duplication of pixels on the landscape and then gaps. So here's, all right, this is not showing up super well, but this is kind of a characteristic image showing Landsat after the scanline corrector failed. So you have, all right, the imager is zigzagging, but when you rectify it all, you get gaps. So this is where the scanner missed on an image like this. Increases in breadth towards the edges of the scenes, but the middles of the scenes can be pretty good. Unfortunately, there's things you want to get that are only on the edges of the scenes. So many regions of the world are cloudy enough that the best pixels are really only found in scenes where the scanline corrector has failed. So without it, we just don't have enough pixels to get cloudless imagery. And it complicates things quite a bit. Complicates things very much. So the result, if we just go through and put those SLC off scenes into our declouding pipeline, we get this. And I think you may be able to make out here, instead of no data gaps bands, we now have these bands of seasonal or interannual incongruity here. It's even more noticeable than this in agricultural regions where you may have these alternating strips of vigorous and non-vigorous vegetation or bare ground. So cosmetically, it's myself, it doesn't bother me that much, but I know it definitely bothers the users who are looking for a pretty map. So our approach to taking, so our second problem is getting rid of these bands. And this is where we diverge from, we're diverging from being, we're no longer a science product here because we're going to actually modify the imagery, but we're going to be as scientific about it as we possibly can. So we do an FFT on the images, find the peaks corresponding to, we're calling them artifacts, but they're not actually like measurement artifacts or anything like that. They're an artifact of the way we're combining the images. Remove them, and then transform the image back. So there's, if you've done this kind of work before, you know that, especially for this kind of landscape, in the Fourier space, it's quite noisy, so we have to do plenty of filtering, and there are peaks everywhere. So modeling the orientation of those gaps, knowing what you do from the satellite's orbit and all, is a pretty key part to removing the peaks we want to remove and not removing other information. And in practice, it's actually looking pretty good. So those are the problems we have. we don't really have off-the-shelf solutions. We can't just go out and buy software that removes these bands from the imagery, right? Perhaps we can, perhaps we just don't want to spend enough money. I don't know. Trial and error isn't our only method, but it's such an important one. It has a huge impact on the requirements for the software. And I'm going to list 3 requirements here. We need to get new iterations of the algorithms into production very quickly so we can see if they're working or if they're failing. We need robust libraries to do the numerical analysis. And then we need to be able to distribute the work. So it's got to, we can't have barriers other than, I guess, essentially typing at the keyboard and spending money to get this thing running across many servers at a time. So we can't really negotiate for licenses and things like that as we go. So for our software stack, let me just keep there. So 3 requirements. The first and the last kind of argue for open source to our team. The first argues, I think, for a high-level language with handy multidimensional array syntax. You can see where I'm going here. The second for LAPACK and GEDL for reading geospatial data. Okay, so the fit for us then is Linux and Python and NumPy and SciPy. All right, now the last thing we need in our stack is software to read and write geospatial data files like GeoTIFFs, and we need to be able to reproject them. We need to be able to warp them and transform them, combine them with other GIS data. The GEDL library has Python bindings, but after years of using them, I've decided that they're not probably production grade for our project. They have a few gotchas, and developing in them, they feel a lot like C++. If you've used these, it's the bindings are generated by Swig from a bunch of C++ files, and I've decided for myself that it's not actually fun to be in Python writing C++ code. So, and one of our requirements is to work at a higher level and have a little bit higher productivity than we would get out of that. So I think we can do a little better. So our requirements then for a raster data library that is a little more in line with what we're used to from SciPy or other Python stuff are 3 more requirements here. We need to be able to read and write ND arrays to and from files. I'd like to use Python types and protocols and idioms instead of C++ constructs and GIS constructs. And I'd like to have programmers free from having to think about memory allocation and pointers and such. I mean, I think this is the one big gotcha from the GEDL Python bindings, that if you take your C hat off, your programs are eventually going to crash and burn. So Rasterio's design then is to be a Python package at the top, Python in the middle for extension modules, and we're using features here like fast loops, memory views, no GIL blocks to release the GIL around parts of the code where it doesn't need to run, and then GEDL's shared library on the bottom. And I'm really enjoying using Python. It's let's see, pardon me. Yeah, it handles, I find it very productive. It handles a lot of the low-level code for writing extensions very well. And it's kind of nice to get the Python 2 and 3 compatibility almost for free if you write code that's a little more in the Python style than in Python style. We don't have Python 3 in production, but I'm not ruling it out. We may in the future. All right, so here's the usage example about importing and using Raster.io to read some data. Oh, that is way too small, isn't it? All right, the gist of it is there's an open method that gives you a file-like dataset object, and it has attributes like Python files do. It tells you whether it's opened or closed. It also provides metadata about the file, the number of bands in it, because the geospatial data typically has multi-bands. You can think of them as layers or something. Methods to get its georeferencing and that kind of thing. Raster.io is, at the moment, is geared towards band interleaved data. So there's a method that reads a band into a NumPy ND array. Whereas I think like in the SciPy's image module is a little more, I think it favors the pixel interleaved, right? So that the array structure is, let's see, rows, columns, and then bands within your image. So ours is flipped around, but it's actually quite easy to convert. Let's see, you can read specific windows out of the data set as well, so using an extended slice-like syntax. So you say, once you've got the file open, you read band and pass it a pair of tuples, and you get a smaller ND array out of that. And then for writing works just about the same way. So to open a data set for writing, you need to pass it a bunch more keyword arguments because you have to, a lot of these GIS raster formats, especially using Legidal, you have to create a lot of the structure up front, and because the TIFFs and whatnot are quite complicated. So you have to pass it the dimensions of the data set and the specific format driver you're using, the data type, et cetera. But I've designed it to be fairly simple to get those keyword arguments by just popping them from another data set. So there's another attribute on a data set where you can say, all right, give me the keyword args I would need to create an equivalent copy. Write band takes another ND array, and you can also write windows back. So there's a fair amount of symmetry, and you can just kind of, I think that makes it fairly easy to understand. If your read and write methods are quite symmetric, and it's a lot less documentation to write. Now for georeferencing, Rasterio follows the read of PyProj, which is a great project that I use all the time, in that its own representation of coordinate reference systems is a dict of Proj4 parameters. Again, I apologize about the size of the code. And I think you can see here. So on the test data set that comes with Raster.io, if you type in, if you look at its CRS attribute, you get the units, the UTM zone, the ellipsoid, etc. All right, so that's reading and writing. Mostly we rely on NumPy for the methods to actually work with the data. We're not going to try to, GDAL has a lot of those built in, but I think we're going to instead rely on NumPy. It just kind of reduces the size of our API and the amount of information you have to keep in your head to use it. There's a couple features added on. I'm kind of overloaded the word feature, but there's capabilities added on to the package on top of reading and writing. And one of them is a features module with a functions where you can, given an array, you can get an iterator over all the features in the array. So these are a feature being a blob of pixels that has the same value. Right, and it yields, it gives, that iterator then gives you GeoJSON-like dicts. So, and then there's the rasterize method, you can turn that around and you can burn those same kinds of features then into an array. And it just uses Python types. There's no data sets, there's no layers necessary, there's no GIS idioms to keep in mind. So just as an example, here's the Python-powered logo. Getting the shapes out of it, here's a little blurb of GeoJSON-like data, and you can burn that back into your raster. Reprojection as well. We can map elements from one array to another using cartographic projections. So given one array and another array, the CRS and the transforms for each, we can use GDAL's algorithms then to warp the imagery over. Also, like it just works on arrays and their georeferencing information. You don't have to have a data set as such. You don't have to have a concepts of layers or anything like that. So that data that you create just out of the blue in a Python program, not in a GIS program, then you can mix that back into your GIS work. So the interesting problems we have that are motivating our choice of Python, NumPy, SciPy, GDAL, and Raster.io. Raster.io is aiming to make GIS more accessible to Python programmers, so we rely on concepts in Python, not GIS concepts. And as well, if you're a GIS analyst these days, you're very often told that your route to a raise and better jobs is to level up on your Python programming. So I'm hoping that Raster.io can be useful to GIS analysts to teach them how to write more idiomatic Python code that's more easily shared with experts, runs a little faster as well. So there's the project's homepage. I hope you'll check it out. Follow the repo if you're interested. We've got a number of contributors already, including, I think, 5 people now writing Python code, which I think is pretty darn good. This is my colleague Amit's blog post about the debanding. So I'm going to have these slides online too. You can check it out. It's a lot more details in there that I could really go into. And thank you very much.
Questions?